Hello everyone. This talk is going to be about real-time neural BRDF with spherically distributed primitives, a neural reflectance model that provides a unified framework for representing a rich diversity of materials. I first give an overview of our method. This work presents a neural reflectance model that is a choice for achieving realistic appearance in real-time rendering applications. Our system is designed according to three principles: efficiency, mild memory cost, and generalization. The proposed method is a unified framework that can represent a variety of materials, which can be used for measured data compression, fitting sparse measurements, physical-based material acceleration, and so on. After the overview, I am going to introduce more details. We start from giving an analysis of implicit neural representation from the feature volume perspective. Feature-based approaches often use differentiable feature primitives to represent the 3D geometric shape. We extend the idea to represent the 4D BRDF. In terms of the geometry or Lambertian effect, feature-based approaches discretize the 3D spatial space into a multi-resolution regular grid and store local features in an octree-based volume, a hash table, or a dictionary. Representing BRDF with such feature-based strategy can be challenging to harness, as BRDF has a higher input dimension, 4D, compared to the geometry. And directly expanding the 3D spatial grid into higher dimension to capture BRDF is prohibitive for its large memory footprint. We propose to alleviate this difficulty through a factorization which decomposes the BRDF to two 3D hemisphere feature grids. However, discretizing the sphere surface is much more complicated than that of a cube volume used in geometry representation, in terms of uniform pixelation and fast pixel indexing, both of which are naturally achieved by the cube volume with regular discretization but pose challenges to the sphere surface. This work identifies the principle of a well-suitable sphere parameterization for BRDF representation, and experiment several choices. Next, I am going to introduce the full pipeline. The sphere is parameterized with HEAL pix. Given the incident direction and outgoing direction, we find the surrounding pixels independently on a spherical index grid. For all resulting corner indices, we look up the corresponding k-dimensional neural primitive from the codebook, which are interpolated according to the relative position within the respective curvilinear quadrilateral pixels. Finally, a tiny MLP takes the concatenated features and outputs final bidirectional reflectance value. Additionally, the neural reflectance primitive plays an important role in our system. It is the key to the memory efficiency. Next, I will demonstrate the experiment results in three aspects: performance, superior quality, and two extension applications. Our reflectance model is memory-friendly and can be evaluated in real time. The neural reflectance primitives offer informative features for each hemisphere component and reduce the complexity of the decoding MLP, leading to fast evaluation. These primitives are centrally stored in a codebook and can be shared across multiple grids and even across materials. Next, we demonstrate quality comparison in fitting reflectance models to measured material. Compared with the previous analytical methods and neural-based methods, our method shows better qualitative results. Our method provides a unified framework that is agnostic to the materials, whether they are isotropic or anisotropic, measured or simulated, spatially varying or not, and whether the sampling is dense or sparse. Next, we demonstrate the first example application: accelerating physically based simulation. Reflectance models designed for photorealistic rendering are often layered. By constructing various interface layers and internal media, these physical methods can cover a wide range of appearances. However, evaluating such models is typically achieved through light transport between layers, simulated by time-consuming Monte Carlo methods. Since our method is agnostic to the internal light layer interactions, it can be directly used for accelerating these physical-based materials. Next, we demonstrate the second example application: bidirectional texture function compression. Tabulating an isotropic BRDF consumes tens of megabytes memory and becomes prohibitive for spatially varying material, impeding the network transfer and runtime loading. To represent the spatially varying effect, a neural texture with 4 channels is used. The convincing results of our method suggest that it can be easily extended for the compression purpose. In a summary, this work presents a neural reflectance model that is a choice for achieving realistic appearance in real-time rendering applications. This work also provides a unified framework that can represent a variety of materials, which can be used for measured data compression, fitting sparse measurements, physically based methods acceleration, and so on. That's all I want to introduce about our real-time neural BRDF. Thanks for your attention.